Let's find the variance and standard deviation of the entire population. Step 1 is finding the mean of the data set. We already have the mean of the population. We found out that the mean was 66. So we've already finished step 1. We've also already finished step 2 because we already have deviations. We already subtracted each number by the mean. We can move on to step 3, which is squaring each deviation. We need to make a new column of squared deviations. We're going to square each of these deviations. What that means is we're just going to multiply each deviation by itself. So first we're going to multiply -6 by -6. When you multiply a negative number by a negative number, you get a positive answer. So -6 times -6 is just 36. You get the same answer that you would have had if you had multiplied 6 times 6. Let's now do it with 18. 18 squared is 18 times 18. So just multiplying each deviation by itself. We get 324. Next we'll just multiply -1 by itself, which will be -1 times -1. -1 times -1 is just 1. The negatives cancel out. -10 times -10. That's the same. That gives you the same answer as 10 times 10. The two negatives cancel out, and you get, well, 10 times 10 is 100. Now we have -1 times -1 again. Which is just 1. So now we have all of our squared deviations. We'll put them in here. So now we finished step 3. We've squared each deviation. The next step is finding the mean of the squared deviations. I mentioned an adjustment here. We actually don't do any adjustment if the data comes from an entire population, like it does here. We just find the mean of the squared deviations. So how do we do that? Well, the mean of the squared deviations will just be the total of the squared deviations divided by 5. It's just the mean of these 5 numbers. So let's add those 5 numbers and divide by 5. Let's add the 5 numbers and then divide. We're going to add the squared deviations and then divide the total by 5, since we have 5 squared deviations in here. So the total is 464. 462. Now we divide 462 by 5, and we get our answer. We get 92.4. So the variance is just the mean of the squared deviations. Just like how the mean absolute deviation was the mean of the absolute deviations, the variance is just the mean of the squared deviations. And it came out to 92.4. Sometimes I like to write out the work like this. For the mean absolute deviation and the standard deviation. For the mean absolute deviation and the variance. And what we just added and divided by 5. Oh, it was 92.4. That was the variance. So to get the variance, we added the squared deviations and divided the total by 5. Because I said if you stop at step 4, you get the variance. If you stop at the mean of the squared deviations, you get the variance. If you go one step further and find the square root of the variance, you get a number called the standard deviation. So this was our variance. If we find the square root of the variance, we get the standard deviation. To get the square root, we can just press the square root key right here. And it comes out to about 9.61. So this is the standard deviation. I can just write STDEV. And remember that this right here was the mean absolute deviation. I'll just write it like this. Now let's try to find the variance and standard deviation of the sample. We've already done steps 1 and 2. because we already have our deviations. We can skip to step 3, which is squaring each deviation. So we need our column of squared deviations. So we'll start with 0, which is the first deviation, and square it. 0 times 0 is just 0, meaning 0 squared is 0. 5 squared, which is 5 times 5, is 25. And negative 4 squared, which is negative 4 times negative 4, is 16, because the negatives cancel out. So we finished step 3, we squared all the deviations. Now we have to do step 4. Remember when we found the variance of the population, we just found the mean of the squared deviations in step 4. But notice how it says if it's a sample, you find an adjusted mean. And the way it's adjusted is actually, instead of dividing by the number of numbers, which would be 3, you divide by 1 less than the number of numbers. That's what makes it an adjusted average, or an adjusted mean. So let's add the squared deviations. They add up to 41. We divide by 1 less than the number of numbers, which means we divide by 2, because 2 is 1 less than 3. There's actually a notation for this. It's actually called n minus 1, because n is the number of numbers, so n is 3, and what we're dividing by is 1 less than n. So we're dividing by n minus 1. And we only divide by n minus 1 if the data came from a sample. If the data came from a population, you just divide by the number of numbers. You just divide by n. 41 divided by 2 is 20.5. That's the variance of our sample. And if you want the standard deviation, you just move on to step 5, which is just finding the square root of the variance. What's the square root of 20.5? We can hit the square root key, and it's about 4.53. So this is our standard deviation. Remember how I said that the mean absolute deviation was higher over here? I mean, the mean absolute deviation was 3 here, and it was 7.2 over here. And The reason why it came out to a higher number with the entire population is because the population had more dispersion. The idea is that with any measure of dispersion, the value should come out to a higher number when the data set has more dispersion, which means that since the variance and standard deviation are also measuring the dispersion, the variance and standard deviation of the population should come out higher, and the variance and standard deviation of the sample should come out lower, because the population has more dispersion and the sample has less dispersion. And let's check to see if that happened. The variance of the population is 92.4, and the variance of the sample is 20.5. So the variance of the population did come out higher because it has more dispersion, and the standard deviation of the population was 9.61, and the standard deviation of the sample was 4.53. So the standard deviation of the population did come out higher than the standard deviation of the sample. The reason why is because the population has more dispersion and the sample has less dispersion. So we can see that anytime you calculate a value to measure the dispersion, the value will come out higher when the data set has more dispersion. Or at least that's true with with all of the good measures of dispersion. The exception was the range. We could see that the range doesn't always come out to a higher number when the data has more spread, but the other three, the mean absolute deviation, variance, and standard deviation, will come out higher when the data has more spread. It'll always come out higher when the data has more spread. Now, since the variance and standard deviation over here used a slightly different formula than the variance and standard deviation over here, there's actually different terms or different words that are used. When you have a data from an entire population and you calculate the variance without using the adjustment in step 4, your answer is actually called a population variance. I can just write POP for population, and if you find the square root of that variance, then your answer is called a population standard deviation. And if you have data from a sample and you do use this adjustment in step 4, your answer right here would be called a population variance. I'm sorry, a sample variance. And when you find the square root of the sample variance, your answer is called a sample standard deviation. So it's just a more specific way of describing these values. So one reason why they use different words is because these values right here are calculated with a population, and these values are calculated with a sample. And another reason is because these values right here are calculated with a slightly different formula than these values over here.